All right, so today's going to be the last lecture for the week. We're going to be talking about section 4.6 in your textbook, which is rational functions and models. We're actually going to be skipping kind of the back half of this chapter, so it's mostly related to story problems. And frankly, I think it's just overcomplicates things a little bit more than we need to. This chapter is already probably going to be the toughest one that we've done so far. I don't think we need to add a bunch of extra stuff in. That's not terribly important. So what we are going to be talking about today is rational functions and asymptotes. The first thing to get down is what actually is a rational function. So hopefully you remember what rational numbers are. Rational numbers are any number that can be expressed as a ratio or basically as a fraction when the denominator is not zero. So effectively, this is anything that is not like a endlessly repeating or an endlessly non-repeating decimal. So something like pi, something like square root of 2, anything that you can write like as a decimal that ends or as a decimal that repeats, or any whole number, any fraction, anything like that is a rational number. With functions, the concept of rational and irrational is very similar. A function that can be represented as f of x equals px over qx, where px and qx are polynomials, and qx does not equal 0 is a rational function. So that our polynomials thing is an important part to keep in mind. So if q of x is not a rational function, or p of x is not by itself a rational function, then this is not necessarily, this won't work. The domain of a rational function includes all real numbers except for the zeros of the denominator. And we're going to talk about why in just a little bit here. So first off, we want to be able to identify rational functions. So first of all, what we're looking for is a polynomial in the numerator and in the denominator. And then, yeah, we just need to make sure that they're both rational functions. So 2x minus 1 is a rational function. X squared plus 1 is a rational function. So this is rational. This one we have 1 over the square root of x. Square root of x is not a rational function. If you graph this and you try to put a negative, it won't work. So this is irrational. And in the last one, we have x cubed minus 2x squared plus 1. That's rational, over x squared minus 3x plus 2 is also rational. Now, like I was just saying, we can also look at the bottom number, the denominator, find the zeros of this, and that will give us our what's it called? That will give us our I can't think of the word. Sorry. That will give us the numbers that don't fit into our domain. So in this case, there's actually, what we do is we find the zeros of this function. So x squared plus 1 equals 0. And luckily for us in this first one, there's no real number that we can put in for x. This is true. If you put in a negative number, it's going to get squared, so it's going to become positive. We could use I, but if you use a complex number, then it's not going to show up on a graph anyway. So this one has a range or a domain of infinity to, or negative infinity to infinity. Right? There's no number we can put in for x that won't still give us an answer that is a number. For this one, g of x, so this one works a little bit differently. Because x can't be negative, x also can't be 0, because if we have 0 on the bottom, we're going to get anything, or we're going to get the square root of 0, which is 0, and 1 over 0 is undefined. So basically, x is greater than 0 for this one, or our range is 0 to infinity with parentheses. The last one's a little bit trickier. We have an actual couple of numbers that won't work here. So in this case, we have x squared minus 3x plus 2. So we want to solve this for the zeros. I'm going to take a wild guess and say that this factors to x minus 2 and x minus 1. Is that right? Get x squared minus 2x minus x. It's minus 3x plus 2. Okay, yeah. So these are the two. This is the factorization of this quadratic, which means that x equals 2, comma 1. These are the zeros. So these are the exact opposite things of what actually happens for our range, so our domain. So our domain here would be x does not equal 2 or 1. We could also say that this is negative infinity to 1, This is 1 to 2. Should be a unity symbol here. Pretend there's a unity symbol there, right here. And 2 to infinity. Personally, I think that's a lot easier to write. I think your textbook also writes it like this for this section, but x cannot be equal to 2 or 1. And the reason is this. If we plug in 2 for x, right, I don't know what we get on the top. We get 8 minus 8, which is 0, plus 1. That's 1, right? So we get 1 on the top. But if we plug in 2 on the bottom, we get 2 squared, which is 4, minus 3 times 2, which is 6. So 4 minus 6, that's negative 2, plus 2 is 0. 1 over 0 is undefined. So we don't have any points that work at that spot. If we plug in 1, we get 1 squared, which is 1, minus 3 times 1, which is minus 3. 1 minus 3, negative 2. Again, plus 2, we'd get 0. Up on top, we'd get also 0, it looks like. So we'd have 0 over 0, which is also undefined. 0 over 0, just as a fun little math thing, is not actually 1. I know that most things, when they're divided by themselves, are equal to 1, and that does not work for 0. This is an undefined situation. Now, we're going to introduce the concept of vertical asymptotes. So specifically, we're going to be talking about asymptotes in general because you may or may not know what they actually are. But what happens when a rational function approaches an x value that is not part of its domain? Generally, this forms what is called an asymptote. And an asymptote is an imaginary line that never quite touches a given function or curve. So an asymptote is not actually part of a function, but it's something that helps us kind of define the function. So in this case, we have an asymptote at, assuming these are all equal to 1, some terrible number that's not actually on one of these lines because the graph is evil. But the point is, there's a vertical asymptote right here, and this curve is never going to actually hit that. And that's because, presumably, whatever the function is has a 0 at this value. So there'd be a 0 on bottom when you get here, making it undefined. Now, we can look at some examples of how these work. But in general, a vertical asymptote exists when a rational function moves towards positive or negative infinity as it approaches a 0 of the denominator. For example, let's consider the function x over x squared minus 1. Now, the zeros of this function are 1 and negative 1, right? Negative 1 squared is positive 1, 1 minus 1 is 0, and 1 squared is 1 minus 1, which is also 0. So what we want to do when we're thinking about these is we want to start from, we have 1 and negative 1, and what we want to do is we want to kind of approach these from the two sides. So what we do is we'll say, okay, as we're coming to negative 1 from the left, so like somewhere around negative 2, what do we get for our points? So if we plug in negative 2 here, we'd get negative 2 over negative 2 squared, which is 4, minus 1. That's 3. So we would have negative 2 over 3. Now, what happens if we put in like negative 1.1? So now we're getting really, really close. We'd get negative 1.1 over negative 1.1 squared. Negative 1.1 squared is like negative 1.2 is 1.21. So we'd have 1.21 minus 1 on the bottom that give us 0.21. Negative 1.1 divided by 0.21 is some positive number close, or some negative number close to negative 5. And then let's see. Why does this have this going up? It's kind of weird. This might not be the right graph. But anyway, then let's say we go to negative 1.01. Now we've got negative 1.01 on our top over negative 1.01 squared times negative 1.01 is what? It's something with a bunch of zeros. It's a very small number. And when we subtract 1 from this, we're going to get some really small number. So let's say it's 0.001 down here. Now we've got like negative 1,000 on the top. So as you can see, the closer we get to negative 1, the closer we're reaching to negative infinity. If we put, we had negative 1.000001 over 0.000000000001, something like that. This number is getting really huge really fast. It's negative, so it's getting really small, I guess. But it's going towards negative infinity, and it's never quite reaching it. So it's never reaching this point where x is 1, or negative 1. Because once you get to x is negative 1, you have negative 1 squared, which is 1, minus 1, which is 0. So that's kind of how the asymptotes work. If we go from the right, for instance, for this one, so let's start at 2, positive 2 this time. We'd have 2 over 4 minus 1, which is, this is 2 squared, so we'd have 3 on the bottom. If we put in 1.5, we'd have 1.5 on top. We'd have 1.5 squared, which is what, like, longhand. Why don't I remember what 15 squared is? 7. Wait. Yeah. So 2.25. So you'd have 2.25 minus 1, which is 1.25. So if you, that's 1.5 over 1.25. So 2 divided by, so that's like 12 over 10. So 1.2. And then let's say we put in 1.01. We'd have 1.01 over, what is 1.01 squared? Let me just use a calculator. So we'd have 1.01 over 1.0201 minus 1. This is 1.01 over 0.0201. 1.01 divided by 0.0201. So this is already equal to about 50. So as you can see, the closer we get to 1 coming from this side over here, right? We started at 2, and then we went to 1.5, and then we went to 1.1 and 1.01. The closer we get to this y, or this x equals 1 line right here, the closer we get to infinity. So we're already at 50 at 1.01. Obviously, if we went to 1.0001, you'd have, some silly number on the bottom, like 0.0000020001 or something like that. And when you reach this point, you're effectively just going to keep getting bigger and bigger and bigger numbers here. So eventually you'll hit positive infinity, but you'll never actually hit this point where x equals 1. Because if x equals 1, you get 1 squared minus 1 on the bottom. That's 0. That's undefined. Now, horizontal asymptotes are a bit trickier to conceptualize looking only at their formulas. We're going to talk about some rules for how to do horizontal asymptotes. They're pretty simple. In general, for these ones, it's also pretty easy. You just find the 0 of the denominator. So whatever's in the denominator down here, set it equal to 0. And that's going to give you your 2 horizontal asymptotes. So in this case, x equals 1, negative 1. These are horizontal or vertical asymptotes, sorry. So at x equals 1 and at x equals negative 1. Now, horizontal asymptotes are a bit trickier to conceptualize. Like I said, a horizontal asymptote is a horizontal line that the graph of a function approaches but never reaches. The previous example showed us 1 at y equals 1. If you plug in this function, that's not actually going to work. This function is graphed horribly. It doesn't really matter. Ignore this. Look at the actual graph. You can see that there's this y equals 1 line going right here, that these two lines never reach. This is not a horizontal asymptote because this parabola is actually hitting 0. And then there's nothing in this section right here because, again, this is a weird graph, but that's not really the point. Point is horizontal asymptote right here at y equals 1. Now, it's going to be really hard to explain how horizontal asymptotes work until we get into an example, which I'll do in just a second. But there are 3 rules for determining whether or not a function has any horizontal asymptotes. The first rule is if the degree of the numerator is less than the degree of the denominator, y equals 0 is a horizontal asymptote. So for instance, if we have x over x squared minus 1. For horizontal asymptotes, this one will have since we have degree of 1 on top, degree of 2 on bottom, and it says if the degree of the numerator is less than the degree of the denominator, y equals 0 is a horizontal asymptote. The answer, or the reason for this is pretty simple, actually. Let's say we plug in 1,000 for x. Actually, let's start with 2. Start with 2 for x. So we have 2 over 2 squared minus 1. That's 3, right? We already used that example multiple times. Now let's try 5. We get 5 over 5 squared is 25 minus 1, 24. So we have 5 over 24. Then let's say we plug in x equals, let's say 100. We have 100 over 100 squared, which is 10,000, minus 1, which is 9,999. Oh, oops, this should only have 2 zeros. And what you'll notice is 2/3 is about equal to 0.66. 5 over 25 or 24 is about equal to 0.22 or something like that. 100 over 9,999 is 0.010001. So you'll notice that these numbers are getting smaller and smaller as x gets bigger and bigger. This is because as x gets bigger and bigger, first of all, this becomes irrelevant, right? When we're talking about the difference between 10,000 and 9,999, that's pretty negligible. And you can imagine if we had x equals, if x equaled 10,000, now we're squaring that, we've got what? 1 with 8 zeros. That's 100 million. 100 million minus 1 is effectively still 100 million, right? Like it makes barely any difference in our fraction. And this fraction is very, very small. It's effectively the same as 1 over 10,000, which is much smaller than 100 over 10,000. So as x keeps getting bigger, we can ignore this. And then we see that x over x squared, that value is always going to be this sort of fraction, right? It's about equal to 1 over x. So as x goes to infinity, this gets closer and closer and closer to 0, but it never actually reaches it, right? No matter what you put in for x here, this is not equal to 0. You can get very, very close, right? You can have 1 over 1 with this many zeros. That's still not equal to 0. It's very, very close, but it's not there. So when you have a numerator with a degree less than your denominator, when x gets really, really big or really, really small, the rest of the numbers here don't really matter. What matters is that this number is getting kind of closer to infinity faster than this one. So you effectively get this asymptote at y equals 0. If the degree of the numerator equals the degree of the denominator, then y equals a over b is a horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. So this one, let's say we have 3x minus 2 over 5x plus 4. What this is saying is that this one, where the degree is 1 on top, 1 on bottom, they're the same. This has a vertical or a horizontal asymptote at y equals 3 over 5. And the reason for this is basically the same. You can imagine if I put in, a million for this, I'd have 3 million minus 2, basically 3 million, over 5 million plus 4, which is basically 5 million. 3 million over 5 million, you can reduce to 3/5. So it gets constantly closer and closer and closer to this, but it's never going to actually reach this value, right? No matter what you do, it's not going to be quite that because you have this weird little minus 2 and this weird little plus 4. So they just barely throw it off enough that you're never actually going to get to 3/5. You can get as close as possible, but you won't ever actually hit it. And then the last one, if the degree of the numerator is greater than the degree of the denominator, there are no horizontal asymptotes. And that one is because as you get, you'd have, let's say you have x squared plus 2 over x minus 1. Right? As you get bigger and bigger numbers, you can basically disregard these, and x squared over x reduces to just x, and x can be any value, right? It can be -30, it can be -5,852, it can be -1, it can be +1, +10, +10,000. It doesn't really matter. So when you get the degree higher on top than it is on bottom, there are no more horizontal asymptotes. Now, we're going to practice identifying asymptotes because I just said a lot of things about asymptotes that are probably awfully confusing. So identifying horizontal and vertical asymptotes in the following graphs. So doing it from graphs is super, super easy. Just look to see where the lines are that these graphs are not quite hitting, and then write the formulas of those lines. So in this case, let's start with our vertical ones on this one. We've got one here, we've got one here. This one is at x equals 1, so we have a horizontal or a vertical at x equals 1. And we have another one at x equals what? -5? -5. So that's this one here. And then x equals 1 is this one here. Then if we're looking for the horizontal ones, we see that there's one right here. Generally speaking, if you get this weird parabola thing in the middle, because it just kind of like gets to right here and then goes back down, it's not really an asymptote. It doesn't keep approaching this spot, so we wouldn't count like, whatever this would be. So we're just looking at this one, which is right in between 2 and 4. So that's probably y equals 3. And that's this horizontal asymptote right here. And remember, hopefully this is review, but sometimes it gets confusing. Remember that if you have an x equals something, that means it's an x value, so it's going to be straight up and down. If you have a y equals some number, then it's going to be y equals whatever that is. So it's going to be horizontal. So your horizontal asymptotes are y equals, your vertical are an x equals. This one, we've got a vertical asymptote right here, horizontal asymptote right here. This one is at y equals, it looks like 1. If I'm counting correctly, 1, yeah. And then this one is at x equals 1, 2, 3. So x equals 3. So as you can see, these ones are pretty easy. Now, this graph right here, they don't actually give me individual lines that show them, but that is because both of them are the axes. So in this one, we have a vertical asymptote right here. So that is x equals 0. And we have a horizontal asymptote right here, which is y equals 0. So you could list these as like, horizontal asymptote equals y equals 3, vertical asymptote equals x equals 1, x equals -5. But if you just list it like x equals 3 and y equals 1, that would be fine too. All right, now we're going to look at how to do it symbolically. This is a little bit tougher, but this is something that I think will hopefully help clear it up a little bit. So let's start with vertical asymptotes. Vertical, and then we'll have a horizontal. And what I'm going to do is just kind of, that's the first one, second one, and the third one. And basically, the way I want to do this is, I think that probably trying to explain the concepts of them is a little trickier than just showing you the math. So we're going to go through the math right now. Vertical asymptotes, remember, exist where the denominator is equal to 0. So in this case, we have 3x plus 3. We're going to set that equal to 0. Subtract 3 from both sides. Now you have 3x equals -3. Divide both sides by 3. You have a vertical asymptote at x equals -1. That one's pretty easy. Horizontal asymptote, we need to go back to our 3 rules. So I would strongly recommend writing these down. If the degree of the numerator is less than the degree of the denominator, our degree of the numerator is 1, our degree of the denominator is 1, so it is not less, it is the same. If the degree of the numerator equals the degree of the denominator, so this is the one we want to use for this one, then y equals a over b is a horizontal asymptote where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. So here, leading coefficient of the numerator is 6. So we have y equals 6 over, leading coefficient of the denominator is 3, or y equals 2. So that's our horizontal asymptote. So really not too terribly hard to solve for. This one, starting with our vertical one, we need to set x squared minus 4 equals 0. Luckily, this one's pretty easy. We just need to set x squared equal to 4. So x equals plus or minus 2, which means we have a vertical asymptote at x equals 2 and x equals -2. So these are our two vertical asymptotes for this. In general, your vertical asymptote number is going to be the same as the degree of the function on the bottom. It's not always the case, but usually it's going to be the case. All right, then horizontal. So we've got a numerator with a smaller degree. Our degree is 1 in the numerator. Our degree is 2 in the denominator. So we're going to use, I believe it's that first rule. If the degree of the numerator is less than the degree of the denominator, y equals 0 is a horizontal asymptote. So easy enough, y equals 0. So that one's done. So horizontal ones are pretty easy. You just got to follow the rules for them, but I know they can be kind of tricky as well. All right, last one. Here's our denominator. We need to set that equal to 0. Easy enough. So we got x equals -1 for this one. Hopefully you all can solve that pretty quick. And then we need to look at the degree of the numerator is 2, degree of the denominator is 1. So we have a higher degree on the numerator. If the degree of the numerator is greater than the degree of the denominator, there are no horizontal asymptotes. So we would do none. Right? And that's how you solve for those symbolically. So I'm assuming there's going to be some questions on the conceptual stuff for this one. It didn't exactly feel good explaining it, so I imagine it's not going to feel good listening to it. But I will try to clear that up in class. Hopefully solving for them helps shed a little bit of light on it. Shouldn't be too terribly difficult, but we will talk about that more in class as well.